Thank you. Thanks for the introduction. Well, yes, hello, I'm Tom. I'm very delighted to be here, and I'm pleased to speak to everyone. I hope you find this topic interesting. Accelerating shared library execution in a DBT. Well, firstly, just a little bit about me. Thank you for the introduction there. Just a quick slide to say what I'm interested in. Yep, lecturer, computer science, University of St Andrews in Scotland. Generally work in the area of computer systems. Core research interests are binary translation, virtualization, OS, all of the systems level sort of cool things. That's what I'm interested in. Right, okay, what's the problem then? What's the problem? So, dynamic binary translation of a program that uses shared libraries leads to a performance deficit. That's the problem. Okay, so let's explore that in a bit more detail. And this graph is showing you that we've got some performance to gain here. Okay, we've got something running under DBT that takes a long amount of time to run, nearly 100 seconds. And something that doesn't use DBT, native libraries, that runs much quicker, 10 seconds. So we've got this big performance gap here that we're going to try and fill, we're going to try and achieve. Right, so let's set the scene a bit. Let's see what DBT is all about. So dynamic binary translation is translating a program compiled for one instruction set into another at runtime. Okay, and this is what DBT might look like. You might have some program compiled for the ARM instruction set. You might have some DBT system running on an x86 machine, and this DBT system takes this ARM program and bit by bit, as it runs it, it converts it into x86 code, and that's how it will execute those ARM machine instructions. Much more efficient than doing something like interpretation. Bit of the terminology that I'm going to use during this talk here. ISA, the instruction set architecture. Hopefully you're familiar with what an ISA is. The host, or the host machine, is the ISA on which the translation runtime is executing. And for the purposes of this talk, I'm going to talk about an x86 host machine. And the guest, or the guest machine, is the ISA which is being executed using dynamic binary translation. And for this talk, I'm going to be using ARM as the guest ISA here. So let's look at this DBT system in a bit more depth and see how it all fits together. Well, we have some program compiled for ARM, which we now know is our guest machine. We've got our cogs for our DBT system running on our x86 machine host. And the typical way that these DBT systems work is they take chunks of the ARM, of the guest program, in chunks of basic blocks. I hope you're familiar with the term basic block. And as those basic blocks are encountered, as they're executed by the DBT system, they're translated by the DBT system into host machine basic blocks, so x86 code cache. And what's interesting, a bit of an implementation detail, is that some of the guest basic blocks are translated to one or more host basic blocks here, and anything that's undiscovered is untranslated. It's very much a dynamic thing, DBT, so it all happens at runtime. Okay, hopefully you're happy with that. And this is what a typical DBT translation runtime loop looks like. We have some guest PC, the program counter, the emulated program counter of the guest machine. The DBT system says, well, does translated code exist in the code cache? Have we already seen this PC before? No. Well, translate a block of guest instructions to host instructions, store that translation into cache, and then execute that block of code. And then hopefully next time round, the translated code is already in our code cache. It's there. We can execute it straight away. And of course, there's lots of clever things you can do to accelerate this as well. You can chain the basic blocks together. But for the purposes, this is the high-level sort of runtime flow of a DBT system. And this is pretty much how QEMU, the state-of-the-art DBT system, which you might be familiar with, actually works. Just this big loop. Okay, that's the DBT side of things. What about the shared library side of things? Well, I think we could all agree that a shared library could be defined like this, a set of utility functions that can be reused by many programs. So examples of shared libraries are libc, the C standard library, or libm, the maths library that you might link your program against. And shared libraries themselves can depend on other shared libraries as well. So like libm might depend on libc, the C runtime as well. So programs can depend on shared libraries, and shared libraries can depend on shared libraries. And this is what a dependency graph might look like between programs and shared libraries. So we've got some program that depends on libc. We've got some other program that has dependency on libc and libm. We've got yet another program that depends on libSSL for crypto stuff. libSSL depends on libc, libz for compression. And there's all this sort of like complex interaction between programs and shared libraries dependencies. The idea is we have these shared libraries to abstract functionality away and reuse that across different programs. Now, how does it fit together with shared libraries and DBTs? Well, DBT systems, in general, they translate shared libraries needed by the program too. So they treat it as just one unit of translation. We've got the program, it depends on a shared library. So the DBT system will translate that program, and it will also translate the shared libraries that it depends on as well. And this happens on demand, as we've spoken about with a DBT system. As calls are made into that shared library is translated as well. And of course, this means that we also need a copy of the shared library that's required compiled for the guest architecture. So we've got some ARM program that depends on libc. That means we also need libc compiled for ARM. The DBT system does its magic, works its cogs, and it translates the ARM program into its program code, and it also translates the ARM libc into its program code as well, into the library code, and we end up with all of this stuff translated together. And the situation is a bit more complex because actually the DBT system, and in particular QEMU, this is how QEMU works, it also needs to translate LD Linux, which is the dynamic loader. So it doesn't do any of this stuff itself, it just looks at everything for ARM and translate all ARM code into x86 code on demand as it happens. Okay, that's how it all fits together. And this is a problem because translated code is less efficient than native code, okay? You know, we're taking from one instruction set, we're analyzing it at runtime as quick as we can, we're generating some host code as quick as we can. We can't afford to do optimizations, so translated code is generally less performant than the corresponding native code. So the observation here is that shared libraries that programs require are usually quite common. So depending on libc, well, libc is a common shared library. Of course it is. It's the C standard runtime. libm for maths, libSSL, libz, libbz2. These shared libraries, they are used by programs, but they're also quite prevalent on host systems as well. They're native versions. So let's use the host versions of those libraries instead of translating the guest versions of those libraries. Right, so this is what it might look like. We've got some program compiled for ARM, which depends on libc. We've got our DBT system, and as usual, it translates the program code into x86. But whenever we see a call into libc, the shared library, instead, we just send that call out to the native version that already exists on the host machine, the x86 version of libc there, instead of translating it like we did before. Okay, that's the idea. Now, this is the mechanism. This is where it gets a little bit hairy, but let's just bear with me on this. This is how shared libraries work in general in an operating system. In the Linux operating system, this is how the shared library stuff fits together. Okay, so we've got an application that depends on libc, and it calls some shared library function. So it calls puts. And puts is what happens when you have printf with no formatting, right? Puts a string. Now, there's this funny thing called @PLT, because the PLT, or the procedure linkage table, is the magic that connects calls in the application to shared library actual code, okay? So the PLT section looks a bit like this. It's got some instructions that when the application calls puts for the first time, it jumps out to some value that's stored in memory, and that value that's in memory is a callback to the next instruction after that. The next instruction after that does a push. That's just how it works. And then this jump here calls into the resolver. And it's the resolver's job to connect this puts to the real place. It's the resolver's job to load the shared library and get it into memory, figure out where the function is, and connect it all together. So the resolver then does this. It gets some data out of the data section. Not too interesting here, but at this point here, we actually go inside the dynamic linker. Okay, so we've gone into this resolver stub code here, and we've entered the dynamic linker, and the dynamic linker loads the dependent shared libraries. It figures out where the function is. Sorry, it's behind this thing here. Load libc, resolve the puts function, and then what the linker does is it fills in the address of the puts function in here, so that next time around, we can jump straight into it. And once the dynamic link is finished, we can go and execute the puts function, and we're done. And then, like I say, next time around, that address has already been filled in previously, so it's lazy loaded, and then we can just directly call the puts function. That's how shared libraries basically work. Now, the key thing that makes this work for a DBT system that translates a basic block on the fly is that there is always a basic block with a known address when calling a shared library function. Okay, so we can detect calls to shared library functions by detecting executions of this basic block address. So whenever our DBT system sees the execution of that PLT entry, we know that we can start sending ourselves off to the native shared library versions. And this is how it starts up. We have to parse the ELF file. We have to look at all the PLT entries. We have to look at the relocation entries. We have to connect them together. We have to figure out what shared library we have. And then we just create this mapping of shared library functions from their guest PC address to the corresponding host function pointer address. Not too interesting what goes on here. See the paper for more details. But effectively, when we load the binary for the first time, we have to detect all of the functions that we need. We have to connect them together, make sure it's all loaded, and figure out what the host function pointer is. And all of this is very much host architecture specific. Okay, and then so our DBT loop then changes to something like this, right? Our guest PC, when we come into our DBT loop, we say, is this a PLT entry for a shared library function? And if it is, if it was part of that shared library function table, we jump straight into that native code. If it's not, then we just do translation as normal. And that's how it works. That's how it all fits together. So we need to translate between the guest's calling convention and the host's calling convention. We need to move the values from the emulated guest registers into real host registers. And this is where the main problem comes in, because functions obviously have parameters and return values. And in one architecture, they have one particular calling convention. In another architecture, they have a different one. So we have to connect them together. So for the example of ARM and x86, we've got our ARM emulated guest registers here, the X registers, and these correspond to function arguments 1 to 6. We need to copy them into the host registers, RDI, RSI, and so on, to make this actually work. And to do that, we need to know how many arguments they are, what type they are. In order to do that, we have an interface description language which helps us out. Okay, so we've got like the puts function there, has one parameter, memcopy has a couple of different parameters here. And this interface description language tells our DBT which of these arguments to copy over for which type it is. Because, you know, like if we have floating point numbers, they go into different registers than integer registers. So that's why we need an interface definition language. Okay, so just to finish off here, the results are pretty promising. It's pretty good speedups. This is sort of like a micro benchmark about floating point operations, and you know we're getting average speedups of 5 times when running these things. So we have a program compiled for ARM using under DBT, calling these math library functions, and then we compare that versus calling the native versions of those functions, and we get massive speedups from that. And then for more real-world benchmarks, things like OpenSSL, we get massive speedups across here for all of the different OpenSSL benchmarks, which are built into the OpenSSL tool. And for SQLite, a popular embedded database, the internal test suite here, apart from test 16, everything is much faster using the shared library acceleration feature. Test 16 is I/O bound, so there's some weird interaction between I/O buffers here, but each of these tests sort of like follow on from one another. So test 16 is actually a clear down operation where it's clearing out the database and getting rid of stuff. Okay, thank you very much. This is just what's coming up in this area. I'm finished now. I'm going to try and get rid of the lid. I'm going to try automatically generating the lid, and I'm going to deal with function pointers, which are a tricky subject. Thank you very much.
Thank you. Time for any questions? Yes. And there is a mic over here for questions.
A very quick question. Thank you for the talk.
Thank you.
In your comparison with the speedups, what is the baseline?
So the baseline is not using accelerated techniques that are presented in the paper. So the baseline is just that application linked against the shared library run under a DBT system as normal, so everything. And then the speed up is when we introduce this connecting to the host native libraries.
Thank you for the intriguing talk. So it can be a stupid question, but did you consider ahead of time compilation because it can speed up everything quite a lot of time?
Sure.
Yep.
That's a great question. So ahead of time, or static binary translation in this particular case, you can't do everything statically, right? There's not enough information statically to be able to do everything, which is why dynamic binary translation is a more prevalent technique for this sort of stuff, because there are things like indirect jumps and jump tables and stuff that you can't actually determine statically at compile time. And so there's a necessary DBT side of things to do. But static binary translation is an interesting thing, and I do have a bit of work in the area of merging shared libraries, like statically into stuff as well. So yeah, it's definitely a thing to consider. Yeah.
I'm asking this question because shared libraries are quite known already before running it. So maybe you can use static things for shared library.
Yeah, I mean, so for shared libraries, that's why this is that's the observation, is that because they are well available, it's likely that you'll have libc compiled on your host machine. So let's just use that instead. Yeah.
Thank you.
Thanks. Hi.
Okay, thank you. So for the talk, I guess that for this to work, the versions of libc that are in the guest system, in the host system, must match the ones that are required by the guest system. Did you have any problem requiring this matching?
There's not really. So the SOAR name stuff is the technical thing. How like the version stuff is done in ELF. So you have to check that the SOAR names match and everything. There is occasionally an impedance mismatch between some structures that are translated between host and guest. We had a problem with fstat where the size of the structure was different between an ARM machine and an x86 machine. So we actually had to discount that. And we couldn't accelerate that one without an additional layer of translation. Now, there are two things that we can do. We can ignore it and then not translate that, or we could add extra mechanisms into the interface definition to say, oh, well, you also need to like adjust the structure layout like that. In general, a lot of functions can be accelerated this way if you're able to find them and test them out.
Thank you.
Thank you.
Thank you for the interesting talk. So I was intrigued by the performance results that you got, which in some ways it makes sense. But I was wondering if you have a feel for why this is the case. So, for instance, in particular, are the x86 implementation perhaps more optimized to begin with? Another way to put this question: if you did it the other way around, do you think you would get the same kind of speedups?
Right. So yeah, and this is actually quite this example here of the micro benchmark of floating point really shows the point. And the reason is for this particular one is that when QEMU translates a floating point operation, it uses software emulation of floating points. Whereas the native version of this library is naturally just using the host, XMM registers, SSE and SSE2 for it. So you instantly get host optimizations for free for this thing. So that's why there's a massive speed up for these things, because you're using the native code for that. Now, these speed ups only occur on functions that are going to be compute bound. Okay, so you spend a lot of time in the native function itself, which is why things like OpenSSL get a great speed up, because the majority of work done here is in the library itself. And so when you call into that library, you're spending all your time running super optimized native code, and that's where those speed ups come from.
So you'd expect to see it essentially the other way around as well.
Exactly,
this,
yeah.
The way QEMU.
Yeah, for sure.
Thanks a lot.
Yeah, thank you. Thanks, great question.
Thanks a lot.
Thanks.